We are going to start module 2 of chapter 9. In this module, we shall discuss the equation of motion of a rigid body. So far, we have assumed that a rigid body consists of a system of particles, but it is better to assume that rigid body possesses unique mass density per unit volume. In such cases, it is better to replace summation by integration. In this module, we shall follow this approach. In this module, we shall discuss linear and angular momentum of a rigid body. Next, we shall obtain the expression for kinetic energy for a rigid body. Equation of motion of a rigid body will also be obtained. Next, we shall define invariable line and invariable plane. Let us first obtain linear and angular momentum of a rigid body. If small rc vector, c is the suffix, be the position vector of the center of mass of a rigid body, then we have rc vector is equal to limit n tending to infinity summation over I equal to 1 to n small mi into ri vector whole divided by capital M. This is defined for a system of particles. Capital M is the total mass of that system. The system contains infinite number of particles, that is a large number of particles. We get this result from the definition of center of mass. If we assume that rigid body consists of unique density, then we have to replace summation by integration. Then we get the result this, that is rc vector is given by 1 divided by capital M into integration over volume r vector into dm. This is a volume integral. If C coincides with O, that is center of mass is at the origin, then we get this vanishes. In that case, R becomes 0, so we get this result. If small p vector be the linear momentum of the rigid body, then we define small p vector for a large number of particles, considering that a rigid body consists of a system of particles, we get this result, that is p vector equal to limit n tends to infinity summation over I equal to 1 to n small mi into small vi. If we assume mass density, then summation is replaced by integration and we get the volume integral v vector into dm. If we replace this small v vector in terms of capital VO vector and omega, we have obtained this result in previous module, then we get this result. We have separated this term and written here. This term has been written by taking capital VO vector out of this integral, since it is independent of integration. Here we have taken omega vector out of this integral, since it is independent of this integration. This gives capital M, so we get this one, and this, from this we get this one. This becomes RC vector. We have used this result here. This can be combined as this. This becomes capital V vector suffix c, where capital V vector suffix c is the velocity of the center of mass. Let us consider the angular momentum of the rigid body. Angular momentum is denoted by capital A vector. We are considering this about the point O. For a system of particles, this can be defined as this one. Since angular momentum is the moment of momentum, so we have Ri vector cross Mi Vi vector. As we are considering system of particles with large number, so I varies from 1 to n and we take limit n tends to infinity. If we assume mass density of a rigid body, then summation can be interchanged as integral and we get the result as this one. Substituting the value of small v vector in terms of this, we get this one. If we split these two terms, and this has been written separately here. Capital VO vector is independent of integration, so it has been written here and this is written as it is. If the point O is fixed, then obviously its velocity vanishes. This gives capital VO vector equal to 0. Again, if O coincides with the center of mass C, then from the definition we get this one. As r vanishes, so this integral becomes 0. In that case, we have angular momentum A vector suffix O, that means we are taking angular momentum above the point O. This is given by integration over volume r vector cross omega cross r. As this term vanishes, we have only this term. We have written this term here. Using the formula for cross product, we can write in this way. This gives r square omega vector. If r has components small x, y and z, omega vector has components omega suffix x, omega suffix y, omega suffix z, then the dot product of r vector and omega vector gives this one. We have written r vector here. Now we consider the x component of angular momentum AO vector. Therefore, we have this is equal to integration over volume r square into x component of omega vector, that is omega suffix x, minus x omega x plus y omega y plus z omega z, x component of r vector which gives small x. After multiplication, we have arranged these terms in this way. If we separate these terms, then we get this result. Omega x is independent of the integral, similarly omega y, similarly omega z. So, taking out of the integration, we can write in this way. This integral gives the moment of inertia about x axis, which is denoted as I suffix xx, Similarly, this gives the product of inertia about x and y axis. This has been written here. This is the product of inertia about x and z axis. This has been written here. Similarly, we can obtain the component x of angular momentum AO vector in a compact form, this one. This is the y component and this is the z component of angular momentum. If we put it in the matrix form, then we get this one. These are the components of angular momentum, x component of angular momentum. These are from y component of angular momentum. These come from z component of angular momentum. This matrix is known as inertia matrix, since the diagonal elements, that is Ixx, Iyy, Izz, give the moment of inertia, whereas the off diagonal elements are the product of inertia. If the body axis system coincides with the principal axis of inertia at O, then the products of inertia vanish, that is Ixy, Ixz, Iyx, Iyz, Izx, Izy will vanish. And in that case, if I1, capital I2, capital I3 are the principal moments of inertia, that is if we denote Ixx as capital I1, Iyy as capital I2, Izz as capital I3, then we have the x component of angular momentum AO vector is equal to I1 omega 1, y component of angular momentum vector equal to I2 into omega 2, z component of angular momentum is equal to I3 into omega 3, where omega 1, omega 2, omega 3 are the components of omega vector along the principal axis of inertia at O. Since here the product of inertia vanishes, so the axis become the principal axis of inertia. Now, let us discuss about the kinetic energy of a rigid body. Kinetic energy T can be defined as half mv square. If we consider the mass density of the rigid body, then this can be written as this integration over volume half v square dm. Putting the value of small v in terms of this, we can write the right hand side in this way. From this square, we get three terms, which is capital VO vector, its square, square of omega vector cross r vector, and 2 into VO vector into omega vector cross r vector. Splitting these three terms, we have obtained this result. Now, we consider two cases separately. First one, here O is fixed relative to the inertial space. Then obviously, the velocity of O, that is VO vector, vanishes. Thus, kinetic energy T becomes, as VO vanishes, so this becomes 0, this becomes 0. So, we get only this term. Here we have written this term. Omega is the angular velocity, it comes from rotation. So, we have written T dot, that is kinetic energy due to rotation. Next case, if capital O coincides with the center of mass C, then r vector vanishes and we get integration over volume r vector dm equal to 0 vector. Using this result, we get this one vanishes. So, we have this term and this term. Here those two terms we have written. This is kinetic energy due to translational motion, this is due to rotational motion. Since VO vector is the velocity of translation. Now, we calculate the rotational kinetic energy separately. T dot equal to half volume integral of omega cross r its square. It gives mod omega square into mod r square into sin square theta dm. Sin square theta can be written as 1 minus cos square theta. Square quantity is always positive. So, we get omega square into r square. Multiplying this, we get first term as omega square r square, and omega square r square into cos square theta gives omega vector dot r vector its square. Now, omega square means omega x square plus omega y square plus omega z square. Since omega x, omega y, omega z are the components of angular velocity along x, y and z axis respectively. Now, omega square gives omega x square plus omega y square plus omega z square. Since omega x, omega y, omega z are the components of omega vector along x, y and z axis respectively, r has components x, y and z. So, omega dot r gives x omega x plus y omega y plus z omega z. We get this result. If we adjust these terms after squaring this one, we get these results. If we integrate these terms separately, we get 6 terms which has been written here. We have already obtained the expression for rotational kinetic energy, that is T dot. Let us take the partial derivative of rotational kinetic energy at first with respect to the x component of angular velocity, that is omega x. Then we get the x component of angular momentum, which is AO vector suffix x is equal to del del omega x operated on rotational kinetic energy, that is T dot. In a similar fashion, we can get the y component of angular momentum vector, that is AO vector suffix y, which is equal to del del omega y operated on T dot, and similarly we can get the z component of angular momentum vector AO vector, which is given by del del omega z operated on T dot. In the previous module, we have obtained the linear and angular momentum for a system of particles. In this module, so far we have discussed and obtained the linear momentum and angular momentum for a rigid body. In this case, we have assumed that rigid body consists unique mass density per unit volume. Now, we are interested to obtain the equation of motion of a rigid body. Let us find the equation of motion of a rigid body. We have already obtained the equation of motion for a system of particles, which is given by capital M, capital R vector double dot equal to capital F vector. Mass into acceleration is equal to force. This is nothing but Newton's second law of motion. In case of a rigid body, the corresponding equation is capital M into capital R vector C double dot, that is capital M into second order ordinary derivative of R C vector with respect to time t is equal to applied force capital F vector. The second order derivative can be written in terms of first order derivative as d dt of capital M R C vector dot equal to capital F vector. This is mass into velocity, which gives the linear momentum. So, this can be written as d dt of small p vector equal to capital F vector. d dt of small p vector is the ordinary derivative of linear momentum with respect to time t. Thus, we have p vector equal to capital M v c vector, small v vector suffix c is the velocity of center of mass of the body. We have already obtained the torque equation of motion in our previous module, which is d dt of capital L c vector equal to capital N c vector, where capital L c vector is the angular momentum of the system of particles about the center of mass, and capital N c vector is the resultant moment of the external forces. In case of a rigid body, the corresponding torque equation of motion remains the same, that is, we have d dt of capital L c vector equal to capital N c vector. Here c is in suffix, c stands for we are taking angular momentum about the point C. The angular momentum of the rigid body L c vector about the point C is given by integration over volume r vector cross omega vector cross r vector dm, r vector being the position vector of an element of mass dm with respect to C. The equation this can be treated independently of the translational motion of center of mass. Here L c vector is given by L suffix x I vector plus capital L suffix y j vector plus capital L suffix z k vector with respect to body set of axes. We have considered that capital Lx, capital Ly, capital Lz are the components of L c vector along x axis, y axis, z axis respectively. We have already obtained this expression Lx equal to Ixx omega x minus Ixy omega y minus Ixz omega z. L suffix y equal to minus capital I suffix yx into omega suffix x plus capital I suffix yy into omega suffix y minus capital I suffix yz into omega suffix z, whereas capital L suffix z equal to minus capital I suffix zx into omega suffix x minus capital I suffix zy into omega suffix y plus capital I suffix zz into omega suffix z. Also we know that total derivative of LC vector with respect to t, that is ddt of LC vector, is equal to del del t of LC vector plus omega cross LC vector. From torque equation we have obtained del del t of LC vector plus omega cross LC vector equal to NC vector about the center of mass. If the motion of the rigid body takes place about a fixed point O, then the torque equation of motion becomes ddt of LO vector equal to NO vector, where ddt of LO vector is the first order partial derivative of LO vector with respect to time t plus omega vector cross LO vector. When expressed in terms of body set of axis, as the body set rotates with an angular velocity omega vector relative to the inertial system. Now, let us define invariable line and invariable plane. Using the torque equation of motion of a rigid body about the fixed point O, we have ddt of capital HO vector equal to capital NO vector, which is 0 vector. HO vector is a constant vector. From this we can conclude it. That is, the magnitude as well as the direction of the angular momentum vector remain constant in space, that is, the axis of the angular momentum is a fixed direction in space. This fixed direction is called the invariable line, the axis of the angular momentum. This is the invariable line. Any plane passing through O and perpendicular to this line or any parallel plane is called the invariable plane. A rigid body is a body in which the distance between any two points remains invariant even when the body is in motion. In our previous module, we have assumed that a rigid body consists of finite number of particles, but it is better to assume that rigid body consists unique mass density per unit volume. Using this approach, in this module we have obtained the linear momentum and angular momentum, kinetic energy of a rigid body, and using this we have obtained the equations of motion of a rigid body.